It's been a short while since I've last been streaming. Almost a week. And there's been some different reasons to that. For that. I think it's pronounced rather. Um, and it's not that I haven't been working on the project, it's just that I wanted to take some time to focus on problem solving and figuring out how to implement a proper algorithm for our physics side of things. I'm reading a lot of books, and something is directly implemented from some of these books. But yeah, sometimes I do mistakes and end up with an unexpected result, or maybe I feel like the presented algorithm is kind of not as elegant as I would like things to be, so therefore I venture off along different paths, combine different methods, and experiment with different different algorithms for handling different stuff. That is why I ended up implementing a GJK algorithm as well as an SAT algorithm. I ended up reading a lot of slides from Dirk Gregorius, I think he's called, at GameDev.net. He he did an awesome presentation at GDC where he lists how to do uh, contact generation, as it's called in physics, on uh, geometry in general. And I use that as inspiration for my own system. So yeah, I did a lot of error checking, swapping around algorithms, trying out uh, one algorithm versus another, and yeah. As you can see, there has been several iterations, and yeah, I wanted to end up with an algorithm that is stable before I use this one, but it had, or rather, this one, I think. Yeah, I think it's this one instead. Yeah, yeah, I ended up using that one. Um, and found that I had made some mistakes in terms of the calculations. I think this algorithm is probably um, in the end more reliable than this algorithm here. And once I got all the bugs fixed, I thought about swapping to this one, which is from the book Real Time, or rather not to this one, to the other one, which is from the book Real Time Collision Detection. An awesome piece of work. There was some errors in the implementation as well as in the actual book. There have been some simple typos where it's usually obvious where you need to change the algorithm. Sometimes you can just Google the alternative. Anyway, it's a really awesome book and very, very usable. Anyway, I ended up wanting to only have certain collisions to handle in the system, so I ended up using the separating axis theorem, but um, for checking an OBB on an AABB, which is what I was messing around with the last time I was showcasing a video, or rather just streaming. I decided to disable the edge detections. This means that we might get collisions which are not actual collisions. From my understanding, the percentage is really low. It's like maybe 5% false positive, and usually we aren't colliding edge to edge, at least not right now, and yeah, I don't find any use for it. The first part is for whenever something collides with the OBB, which never happens since we're only doing collision checking between the OBB, represented by a player character, and all the static AABB, which is Bs, which are the environment. So we usually end up in this place where we have a face vertex or face-face collision, and we usually skip the edge collisions for now. I will implement a method that handles that, but yeah, since I disable this part of the algorithm, we won't end up in that scope. So we end up here where we have a collision with a face of an AABB. And as I've shown you in the last episode, I find the vertices of the OBB that are penetrating the AABB. I use that as contact points. I calculate individual penetrations for each contact point, since I find that that gives the more precise algorithm. We could actually move this. It's a bit more work, but really, since the algorithm already calculates a lot of the needed implementation, we only do a small dot product uh, and do some math around how to use the plane we defined up here in terms of calculating how far the actual vertex of the OBB penetrates at that specific point. So yeah, each point gets assigned a specific penetration, and then we actually move the contact point up to the surface of the contact, meaning that the contact point lies on the face of the AABB. I'm unsure whether this is helpful or not. Anyway, that is the algorithm. So it's basically a very, very simple plane clipping, vertex clipping method, which only works when the OBB is that's much smaller than the AABB, which in our use case right now is true. I will of course have to change all this into a more robust and generalized method. Um, and make something scalable. But as for now, for creating test cases and delivering information for us to develop a physics algorithm upon, it's fine for now. So yeah, that's work ahead of us. Work for another day. Because it's not the only thing I've changed. And if you ever stumble upon this video in the future and would like an elaboration, I can surely give you one. Just let me know. This is more like a journal of sorts, but I do think that I want to help out as much as I can, and if anyone ever ends up watching any of these videos, um, I'll be happy to help out. Yeah, most of the code in the SAT here is the same as always, since I haven't updated this part and I'm only using this part, and this part is currently unused. This is the part of the algorithm that is new. Of course, I might not have shown the function that finds the vertices of the OBB. It simply calculates each of the 8 vertices for this specific box. This is the algorithm for that. You could do this at an earlier step and simply cache the points and perhaps transform them all by matrix multiplication by the transform eventually. Anyway, yeah, there are several ways of optimizing all of that, but yeah, right now I have focused on implementing something that is testable and works, and not something that is scalable or optimized. So therefore, this is the current algorithm. I suspect that I will be using a similar algorithm, at least for creating the box vertices correctly oriented in space. Yeah. Yeah, I'll do that. I just realized this is in a stupid order. I would have preferred to make it XYZ as down here. Anyway, it doesn't matter. Could always swap them if I wanted to. Sorry for the distraction. Anyway, as mentioned, this is like a support function in a GJK algorithm, which basically just fetches the vertex. And you would like to pre-cache the vertices and not calculate them every time this function gets called, so you just pass in the actual vertex array and make it more dynamic, so that once you have a vertex array, you can just pass it in. It doesn't matter what the shape is. It just finds the points that are on the actual plane. Yeah, and return them in a list. But yeah, that's the function. And uh, um, hmm, so yeah, we grab the points, calculate the specific penetration of that point by using the plane that we use for cutting off the vertices. Yeah, I also already mentioned that previously. Anyway, so yeah, this part of the system got changed. I cleaned out all the existing physics code and replaced it with something else. The old physics system is still intact, but it's particle based and doesn't handle rotations at all. So in rigid body physics, we have something called inertia. Uh, which relates to conservation, or no, not conservation, relates to angular momentum. So yeah, our system needs so-called inverse tensors, or rather inverse inertia tensors. Okay, this is spelled wrong. Anyway, and they have to be transformed. A tensor of this kind is a symmetric matrix, and I spent actually 2 days realizing that my math was completely wrong. I originally only did a matrix by matrix multiplication, but that is wrong. If you want to actually rotate the basis of a matrix, which it's called, a rotation of the basis means that the coordinate system of the matrix, which are the first 3 rows/columns, depending on how your matrix is oriented in terms of storage. Is it column major or row major? Anyway, the first 3 kind of vector slots where you have 3 data points describe the so-called basis, which is the 3 perpendicular axes of the coordinate system. So the inertia tensor is symmetric and represents how much an object is allowed to rotate around the 3 axes of the object. It allows you to make objects that are, for instance, elongated and are able to rotate more freely around certain axes rather than others. So yeah, you represent that by a matrix. Some people just represent it by a list of numbers. Yeah, but this is a matrix which can hold uh, more information than just how the object rotates around a certain axis. So therefore, yeah, it's implemented this way in a 3x3 matrix. But yeah, when you want to transform that from, usually it's represented in body space, meaning that each object has its own coordinate system, its own X, Y, and Z axis. And that coordinate system, when the object rotates, for instance, a rigid body might be oriented in some weird way in our world. Then the local coordinate system of the body doesn't change, but the kind of translation, here I talk about the verbal process of kind of translating something from one language to another, i.e. a coordinate system to another. It has to be done by matrix transformation. So how do you transform or rather interpret the coordinate system of one thing into another? You use matrix multiplication. Usually with vectors, you just change the vector by the matrix, usually a 3x3 matrix, because rotation is represented by the change of basis vectors, i.e. the coordinate system of the vector. But once you have a matrix, if you want to change the basis of a matrix, you have to do a multiplication by the want to transform, and then a multiplication of that result with the transposed version of the transform matrix. If you don't, the matrix will be ill-formed and the basis won't be changed correctly. So I spent literally 2.5 days trying to find a bug in the physics system, which resulted in things just suddenly flying off like rockets, and building momentum, or rather velocity, up and up and up for each frame. Usually when the object wasn't rotating or anything, just when it was supposed to lie steady on the ground, it started building up velocity and eventually exploding somewhere. So yeah, it turned out that I had missed how to transform the inverse inertia tensor. Lesson learned: if you want to change the basis of a matrix, remember that you have to do more than just multiply by the actual matrix. You have to also multiply by the transposed matrix, which in a 3x3 rotational matrix is actually the inverse of a matrix. So you might end up in a situation where the transpose is not sufficient. If you have a 4x4 matrix, you would have to not only multiply by the actual matrix, but you would also have to multiply by the inverse matrix. Of course, it doesn't make sense to multiply a 4x4 by a 3x3 matrix. That's not possible. So it would definitely relate to something else than the actual inverse inertia tensor. But anyway. And if you're getting a headache by listening to all of this, I'm sorry. I just feel so much relief after being free of speculating on that. Anyway, be sure to get your math right, know what you're doing, unlike me, who's a total idiot and will have to learn the hard way. Yeah. Anyway, to do rigid body transformations, you have to translate the inverse inertia tensors into world space coordinates, not body space coordinates. We do physics integration as before. The only change here is that I store the force that is applied during this integration step in a buffer, since I clear the forces after they have been applied to, or rather translated, into velocities and rotational forces, or rather rotational velocity. I mean, it's translated into torque. And as you can see, we use the inertia tensor to know how much an object is allowed to rotate around a certain axis, meaning that if the force is on the x-axis, you have to figure out how much does that translate into actual velocity. Anyway, we integrate as almost as before. I changed the collision detection algorithm. Now I only store what is called collision contact data. And this is simply a struct that holds different information. It might change in the future, but yeah, right now I cache some different information in terms of how to handle or rather what information we have about a certain contact, meaning a point in space where actually the OBB penetrates an AABB, because inside our algorithm here, we generate a list of points, we calculate the individual penetration depths, and we store the penetration depths in a list, one for each contact. But then we also pass out information about the actual location of the point, offset by the penetration specifically for that point, so that we get up to the surface of the penetration. And then we store the contact normal for all of the points. And we of course pass out the, let's just disable this or close this for now so we don't get confused because we're not using it. So yeah, we pass that out to the calling function, or rather the calling scope, by these out specifiers. We have 3 outputs, we have 3 inputs. Anyway, so we pass that out to the collision checking algorithm, which is basically this right now, which checks our OBB and our AABB static objects, and we iterate over all these static objects, and we simply set up some data structures here for this specific iteration, and we call our method and get our contact information. If it doesn't get an intersection, we simply just skip the next step. Then for each contact point, we store what did we collide with. I haven't used that except for debugging, so if we don't end up in a situation where this is needed to be known, we will just simply remove it. We also do not need the contact count. That was also for debugging. That is probably going to get removed. I'm not sure. Then we have a contact point. A specific contact is defined by a specific contact point. We have a so-called contact normal, which I already mentioned. That is the same for all contact points of this specific collision. And then we give it the appropriate penetration depth for that specific contact. We generate a list of contacts, which gets passed to the calling scope, which is here. So yeah, we store the data in a list of contacts. Then we start our we have a lot of different stuff here I used for debugging. Anyway, let's just move this. It's definitely not used anymore and probably totally wrong. I'll just move it. Let's see, where did I introduce an error? Anyway, as you can see, I dump everything down here. It's more than half the thing. Eventually I'll delete it, but right now I save it for later. Anyway, as a step before our physics engine, quote unquote, does anything, we do some pre-calculation for each contact. Right now we have a potentially long list of different points where the OBB collide with something. We want to pre-calculate some information stored in that contact, which was some of the fields that you saw before in this struct, where we can store different information. So one thing is the relative position of the contact compared to the center of the OBB. One is the so-called contact transform, which is a matrix that contains the basis, as I used before, as a way to categorize the X, Y, and Z coordinate system. Right now we have some waste because I do not have a math-friendly 3x3 matrix. It would have to be represented by 4 registers, or even maybe just 3 registers, and using the fourth ad hoc. We might do that for optimization. Anyway, right now we return a 4x4 matrix as it fits in our math operations, and we're not that challenged in terms of yeah, we're not challenged right now in terms of memory utilization and optimization. We store everything in column major order. Right now I find that, let's see, maybe I need to test whether this is still relevant after I actually, yeah, it's still relevant. The way our matrix multiplication works right now, it wants the transposed version. Anyway, we store that. We calculate the closing velocity of at the contact point. We translate that into contact coordinates, meaning in contact coordinates, x is the direction of the contact normal, meaning whatever contact normal we have during a collision, it's always up. That is pretty handy because our contacts might be oriented in vastly different ways in space. I could collide with the floor, I could collide with the ceiling, I could collide with the wall, and the contact normal for that contact would point in an indefinite amount of directions. Usually right now we only take the face normals of objects and use them as contact normals mostly. There are some cases where we do something else, but in general, you could say that, or rather, no, we always do that, but yeah, the faces might not be perfectly aligned with some other plane in our, or rather, might not be perfectly aligned with the actual mm, planes of our world coordinate system. So yeah, it might be pointing in a weird way in world space. In a way, for us to handle calculations, it's far more easy to just transform that into a known coordinate basis, so where x is up, y and z are the planar dimensions. So we do that with the closing velocity, meaning that right now during our collision, when one object collides with a static object, the object actually collides with a so-called closing velocity, meaning it moves towards the object with a certain velocity. We translate that into the coordinate space of the contact. We also apply some, or rather add some information about how much force was applied during this integration step, which was the field that you saw before that I added to the physics struct, and then we work out how much acceleration based velocity we got from that force, and we also translate that into contact space, and we simply say we're not interested in the part of that force that is related to gravity, meaning up and down. And since in contact basis the x component is actually up, we set that to 0, and we add these two forces together, and then we know at this contact point this specific object is moving relative to the center, is moving with a certain velocity. We use that to calculate a so-called unit version of the velocity at the contact point, meaning that how many units of velocity would have to be applied to correct this collision. Right now we have a restitution of 0. Restitution is a factor that controls how bouncy the interaction is. Right now it's hard-coded at 0 because we're only colliding with static objects. I do not expect physically static objects to move anywhere when they're collided with. They have sort of infinite mass. Imagine colliding into a wall. It doesn't in reality seem to move a lot. And I say it doesn't seem because it does move. It compresses and it um, applies a force the other way. You might not be bouncing a lot when you hit the wall, but there's a bit of force. If it was a sticky surface, you would have a restitution of 0 because it doesn't bounce. It actually makes you kind of stick to it. Yeah, anyway, if I wanted objects to bounce off the walls, I would increase the restitution into a certain amount. Whenever the x component of this pre-calculated contact velocity is appropriately low, I know that I probably only have to deal with gravity, meaning that most of since the actual force from the previous integration step got cancelled out, I might be dealing with the velocity-based influence of gravity. Therefore, if only gravity is applied to an object, I know that it's probably lying still, or yeah, it hasn't been accelerated up by gravity for a whole lot of frames. I mean, if it's kind of close to 1 tick of gravity, it's probably not free floating in the air and gaining acceleration and thereby velocity. So therefore, I do not want it to bounce anywhere. It would look weird if still lying objects were able to bounce off anything. Anyway, I thereby calculate a this desired velocity I want out of this collision in contact coordinates, and then I pre-calculate that for every contact. Then I do penetration resolving. I'm not gonna step through the algorithm. I think I went through it in the last episode, and the only thing that it behaved weirdly was the actual rotation, because the matrix was not calculated correctly, but it kind of worked. Objects were still able to kind of sink into each other, which I think kind of got fixed. Yeah, so this algorithm hasn't changed, but of course it has changed in the way that it's applied, because the inertia tensor gets transformed in a different way. I'm just gonna move all these comments because I do not need them. Yeah, so this is pretty much the same. The only difference is that I've implemented a so-called iterative impulse solver. This is just pertaining to the actual penetration resolution, but as you can see, we have 5 iterations where, let's see, 5 iterations where if the penetration is lower than a specific margin, I don't care about it and I skip it. Once I do penetration resolution here for a specific point, I iterate over every contact and calculate how much uh, penetration that linear and angular change might have resolved in a different penetration, meaning that um, you might end up in a situation where something potentially penetrates something. Maybe we moved it too much, maybe we didn't, and therefore we iterate over it by several times to calculate whenever we have a kind of stable resolution to as many points as possible. Of course, if they uh, do not penetrate by a lot, we simply skip them, but we might end up in a situation where something suddenly penetrates more, and then we would like to catch that in a later iteration. Of course, if the uh, penetration got resolved, everything is fine and dandy, and we simply just end up skipping most of this loop. You can see here it's calculated along uh, um, the expected change in position at that other contact point. And we subtract whatever penetration we have by, or rather along that contact normal, meaning that if we moved something up along the contact normal out of penetration, good. If not, we might have to iterate over it again. Anyway, in between, just for good measure, I update the matrices of the objects, since, as you can see here, we might change the position and the orientation of the objects, meaning that the matrix, transform matrix, would actually have been changed. Therefore, I updated. I'm not sure you actually have to need to, or rather need to, but yeah. That's what I've done. And then I, of course, update the inverse inertia tensors by applying the new transform. And then we get to the last step, which really, really was where I got stuck and had to find out what on earth was happening. Since I didn't know that I had ill-formed inertia transform slash matrices, or rather inverse inertia tensors. So yeah, I ended up doing this. Let's see, let's just rescope it. I have disabled the scope because I needed it to debug it. I usually do scopes here in terms of allowing overlapping variable names. Anyway, let's just remove all of this garbage here. It's from debugging, and it actually works kinda as expected, and I can explain why it doesn't work in certain areas because there's more work to do. Anyway, let's see. I'll just remove a lot of this. The debugging statements are fine. Yeah, and I also implemented an algorithm that allows me to print a register, or rather a vector, with just a few words of code. Yeah, sorry, me doing the cleaning on stream is just how it is. Yeah, actually I think I will use these ones since we do not need the more elaborate functions. Let's remove that. Let's remove that, and then we end up in a situation where this is debugging. There we go. So now everything is kind of clean. So yeah, we have an iterative solver here as well. We do the same thing. If the desired change in velocity is very low, we kind of skip that object, or rather velocity, because it doesn't seem like we would benefit anything from adjusting it. The objects might be even separating, meaning that this might be negative, and therefore we don't want to mess that up. Anyway, we calculate the amount of torque, or rather, we calculate the required impulse in terms of angular correction and physical, no, a linear correction that is needed. Oh, oops. Linear correction that is needed to move the object in the correct direction, and we simply calculate the required impulse at the contact. Right now we're only handling forces along the contact normal, meaning that we have no friction, which I also stated here. That is the reason why things look weird. We have no friction. We need friction for things to look correctly. So right now we only handle velocity corrections at 1 out of 3 axes. We of course need to correct that eventually, which was my original intent with this episode, but this ended up being me explaining what on earth I've been doing since the last episode. Hopefully we will get to at least some part of the uh, coding for today. Yeah, this is also why I do some work off stream, because I end up explaining a lot of different stuff and feeling like I have to explain what on earth I'm doing. And when I'm thinking about with these things, and when I don't understand everything that is going on, it kind of distracts me from actually solving the problem. So yeah, you have to bear with me in terms of that. If you would like for me to just do some of this off stream in silence, let me know. Right now, I don't think anyone is interested. Anyone are interested in that? Is I? Yeah, I don't know. Anyway, enough talking. Let me just remove that as well. I'm gonna dump it here. Anyway, so yeah, we calculate the expected impulse at the contact coordinate system. We use that to generate a impulse. First, we translate it into a world coordinate space. We figure out how much torque we want to apply in terms of yeah, how much torque we want to apply. We translate that into the actual rotational velocity. We translate the impulse into actual linear velocity, and we add the actual change in velocity, both in terms of, whoops, yeah, I've just saw that had changed, and we simply add it to the object. I'm going to save this for later, because we're going to work in this part of the algorithm when we have to handle friction. But we might pass along values that are needed to debug. You can see here, I started realizing that something was wrong with the tensor, inertia tensor. Anyway, as with the penetration handling, we calculate a specific delta velocity in terms of other contact points, including this one, and we then update the actual. Yeah, I used a temp variable here. Might change that. Yeah, I wanted to be able to debug parts of this, so when I was searching for what was the problem. Anyway, as before, we do a new calculation on what expected velocity correction would be needed uh, after we updated the contact velocity. We can use it to update the expected change in velocity in unit terms. And we do that for every contact, and then we iterate over them again to see if we need to apply more corrections. And that is basically our iterative solver of the whole physics system. So yeah, the next part is implementing friction, but you might ask, so how does it look? And I'll show you. Yeah, I removed the old bounding volume of this one since it was not an AABB anymore. It was perfectly changed into this OBB that is allowed to rotate. So now I can shove the object. I changed the inertia tensor, so as you can see, uh, the object. Hello. Yeah, he's fine. He just needs a little friction. Anyway, as you can see, the new physics system uh, handles rotation. Whoops. Okay, we have a bug here. Um, let's see. Yeah, I know why. It's because it actually uses part of the algorithm that I've disabled, so it doesn't handle those edge cases very well. Anyway, as you can see, I can slam him into the wall, and he kind of separates. He also rotates a bit from the actual, and he doesn't go through the wall anymore. Uh, and I don't know. I haven't given him a name. I know you are good at naming stuff, so maybe you can name him. So yeah, as you can see, he constantly slides over this wall. So we definitely need some friction in terms of making this not look totally weird and not him get him from floating through space and rotating weirdly. uh, but yeah, as you can see, once he gets pushed out of the ground, mostly Paul, that's a good name. I like it. He will forever be known as Paul. But yeah, that is the state of the physics system. It doesn't go through anything, and yeah, most things seem to work. Yeah, right now it looks kind of weird. There's still some stuff to do, but mostly it works okay. At least we do not have any weird penetrations going on. Not extremely weird, that is. Um, and once I get to draw the actual box that is around him, which handles the collision, it might look more reasonable. But yeah, this is the physics system state. Yeah, yeah, I will implement balls afterwards. And shoot the balls into Paul. But yeah, so we need to implement friction. And since we're working in not only one axis but three axes now, we need to instead do calculations in terms of matrices. The problem is that we want to be able to cross a vector, the contact normal, by sort of another vector. But once you... Oh, congratulations. That is great. Let me just make a cut on the YouTube series. Yeah, so in the next episode, I will be continuing on implementing the actual friction. Hopefully you found this tour of the physics system helpful.